Now students, today, at the end of today's lesson, you should be able to 1. Explain the strength of an elastic material. 2. List and explain the energy stored in an elastic wire. And lastly, solve some calculations on the strength and energy stored in an elastic wire. Strength of an elastic material. The strength of an elastic material is described as follows. 1. Tensile or compressive stress. Stress is a quantity that describes the magnitude of force that causes deformation. Stress is generally defined as the ratio of force or load to its cross-sectional area. So, when force pulls on an object and causes its elongation, like the stressing of an elastic band, we call such stress a tensile stress. And when force causes a compression of an object, we call such type of stress a compressive stress. So, stress is measured in Newton per meter square because it is force divided by area. 2. Tensile or compressive strain. When an object or medium under stress becomes deformed, then the quantity that describes this deformation is called strain. Strain is given as the ratio of extension to its original length of a wire. Therefore, strain has no dimension at all. In other words, strain is equal to extension over length. 3. Young modulus. Young modulus is the ratio of tensile or compressive stress to tensile or compressive strain. Hence, the elastic modulus for tensile stress is called Young modulus, and it is denoted by E. And it is measured in Newton per meter square. So, when you have your elastic modulus or Young modulus, which is denoted as E, and we have our tensile stress, which is force over area, divided by our tensile strain, which is extension divided by length. By simplifying this, you end up having your area of your Young modulus as force times length divided by area times extension. And 4. Force constant. Force constant is the amount of force that causes a unit extension of an elastic material, or it is the ratio of force to extension of an elastic material. Force constant is denoted as K, and it is measured in Newton per meter. From Hooke's law, we have force is equal to force constant times extension. By making K, which is the force constant, the subject of formula, we end up having it as F divided by E, which is force divided by extension. Now let's take a look at an example in order to buttress our explanation. A wire of length 5.0 meter and diameter 2.0 millimeter extends by 0.25 millimeter when a force of 50 Newton was used to stretch it from its end. Calculate the A. Stress on the wire, B. Strain on the wire, and C. The elastic modulus of the wire. In order to solve this, tensile stress is equal to force divided by area. And when we want to calculate the area of a spring or the elastic material, because we know too well it's a spring, we use our area, which is equal to pi r squared, which is the area of a cycle. We know too well that from the question we are given diameter as 2 millimeter, and half of a diameter is our radius. So we divide the diameter by 2 to get our radius as 1 millimeter. So we have to convert our radius, which is 1 millimeter, to meter. By so doing, we divide it by 1000. And when that is done, we have our radius as 0.001 meter. And if we recall, our area equals pi r squared, where pi is equal to 3.143, and our radius is given as 0.001. So by substituting it into it, so we have it as 3.143 times 0.001 squared. So we have our area as 3.143 times the square of 0.001 square will give us 0.000001. We now have to multiply the value by 3.143. So we now have it as 0.00003143 or 3.143 times 10 raised to the power of minus 6 meters squared. Recall, stress is equal to force over area. And our force is given as 50 Newton. So we say 50 divided by 3.143 times 10 raised to the power of minus 6. Then stress will now be given as 1.591 times 10 raised to the power of 7. The other value we have to find is our tensile strain. Our tensile strain is extension divided by length. And our extension is given as 0.25 millimeter. So we have to convert it to meter by dividing it by 1000. So our extension will now become 2.5 times 10 raised to the power of minus 4 meter. Our length from the question was given as 50 meter. So we substitute the value of our extension, which is 2.5 times 10 raised to the power of minus 4, divided by our length, which is 50 meter, into the equation. Then we now have our tensile strain as 5 times 10 raised to the power of minus 6. And lastly, we are asked to find the elastic modulus. And when you are asked to find the elastic modulus, you are also referring to your Young modulus. And Young modulus is given as tensile or compressive stress over tensile or compressive strain. And from the calculation we just derived, our tensile stress is given as 1.591 times 10 raised to the power of 7. And our tensile strain was given as 5 times 10 raised to the power of minus 6. So we substitute it into this equation, we end up having our Young modulus, which is E, to be equal to 3.182 times 10 raised to the power of 12 Newton per meter squared. Now let's now move on to our next line of discussion, which is energy stored in an elastic wire. When a person jumps up and down on a tarpaulin, it is clear that the bed of the tarpaulin stores energy when it is in a state of tension. The energy is converted to kinetic and potential energy of the jumper when the tension is removed. Similarly, when a piece of elastic in a catapult is stretched, energy is stored in it, and when the catapult is fired, this energy is converted into a kinetic energy of the projectile motion. So, what actually happens within some of this material mentioned may be quite complex, but we can calculate the energy stored in a stretched metallic wire where Hooke's law is obeyed as follows. The work done by force is equal to the energy gained by the wire. Therefore, work done is equal to average force times extension. And when we say average force, it means force divided by 2 times extension. So we have it as 1 over 2 times force times extension. Since we have our force to be equal to force constant times extension, hence, by substituting the value of our force constant into the initial equation, which is 1 over 2 Fe, we end up having our work done as 1 over 2 Ke squared. Or you can take the energy stored per unit volume of a specimen as 1/2 stress times strain. Let's use the following example to buttress further. Find the work done when the force is applied and a string resulting in extension of 20 meters if the spring has a stiffness of 500 Newton per meter. From the question, we have our force constant, which is given as 500 Newton per meter. The extension from the question is given as 20 meters. So we call our work done, which is given as 1/2 KE square, which is force constant times extension square. So we substitute the value of our force constant and extension into this expression. So we end up having our work done to be given as 1/2 times 500 times 20 square. So the square of 20 is given as 400. So our work done is now given as 1/2 times 500 times 400. So when this is simplified, we end up having our work done to be 100,000 joules or 100 kilojoules. The second example given to us is if a force of 100 Newton stretches a spring by 0.1 centimeter. Find 1. The elastic constant. 2. The work done in stretching the spring, 0.3 meter, if the elastic limit is not exceeded, which means if Hooke's law is obeyed. In order to solve this, our force is given as 100 Newton, while the extension is given as 0.1 centimeter. To convert centimeter to meter, we have to divide it by 100. So by dividing it by 100, you end up having your extension as 0.001 meter. What we are asked to find from the question, the first is our force constant, which is the elastic constant. If we recall, force is equal to elastic constant times extension, that is from Hooke's law. So we substitute the value of our force and our extension into the equation to end up having it as 100 is equal to K times 0.001. By making K the subject of formula, so which means by dividing both sides by 0.001, we end up having our K to be given as 100 divided by 0.001. And when that is done, our final answer for our elastic constant will be given as 100,000 Newton per meter. 2. We are asked to calculate the work done in stretching the spring 0.3 meter. So in order to calculate this, work done from this part is given as 1/2 KE square. So we have to substitute the value of our force constant and our extension given into this expression. You can still decide to use the formula 1/2 Fe since the force has been given. Since you know your force and you also know your extension. So, by substituting the value of our force constant and our extension into this expression, we end up having our work done to be given as 1/2 times 100,000 times 0.001 square. When 2 divide 100,000, we end up having it as 50,000. And the square of 0.001 square will give us 0.000001. So by multiplying both together, we end up having our work done as 0.05 joules. Now students, in today's lesson, we have been able to explain the strength of an elastic material. We also list and explain the energy stored in an elastic wire. And lastly, we solve some questions on both the strength and energy stored in an elastic wire. Now students, the following questions are meant for you to solve. Kindly solve this and send your solution to the school email. Thank you for watching. Hello